Welcome to Learning Outcome 5, our last one, where we meet probability distributions, the patterns that describe how the outcomes of a random situation are spread. We'll look at two discrete distributions and one famous continuous one, and by the end, you'll know which to reach for and when. And let's start with the language. A random variable is simply a quantity whose value depends on chance. The score on a die is a perfect example. A probability distribution then lists every possible value alongside the probability of each. Whatever the distribution, one rule always holds. All the probabilities must add up to 1. And these distributions fall into two families, discrete and continuous, which is the distinction we'll build the whole outcome around. So what's the difference? A discrete distribution takes separate countable values, 0, 1, 2, and so on, like the number of faulty items in a box. A continuous distribution can take any value across a range, such as height or weight, things you measure rather than count. And a probability distribution, remember, is just a rule or table giving the probability of each possible value. Counted versus measured is the quick test for discrete versus continuous. And the simplest distribution is the discrete uniform, where every outcome is equally likely. A fair die is the classic case. Each score from 1 to 6 has a probability of 1/6. A fair coin is another, heads and tails each, with probability a half. Drawn as a bar chart, it's completely flat, every bar the same height, which is its signature. It models fair, symmetric situations, a fair spinner, a random lottery digit, that sort of thing. Let's make that concrete with a fair six-sided die, calling the score x. The probability that x equals any particular value, x, is 1/6 for every x from 1 to 6. As a check, 6 lots of 1/6 add to 1 exactly as they should. The mean or expected value is 1 plus 2 plus 3 plus 4 plus 5 plus 6, all divided by 6, which is 3.5. And the probability that x is greater than or equal to 5 is the probability of a 5 plus the probability of a 6. That's 1/6 plus 1/6, which is 1/3. If we picture this distribution, each of the 6 scores has the same probability, 1/6, so all 6 bars stand at exactly the same height. And that flat profile is the hallmark of a uniform distribution. The total area, meaning all the probabilities added together, still comes to 1. Real-world examples are all around: a fair die, a fair spinner with equal sectors, or a single randomly generated digit. Whenever every outcome is equally likely, this is the shape you get. Next up, and a real workhorse, is the binomial distribution, which counts the number of successes in a fixed number of trials. It applies whenever 4 conditions hold. There's a fixed number of trials, which we call n. Each trial has just 2 outcomes, success or failure. The probability of success, p, stays the same every trial, and the trials are independent of one another. Tick all 4 boxes, and you've got a binomial situation. The formula looks busier than it is. The probability of exactly k successes in n trials is cnk times p to the power k times, in brackets, 1 minus p to the power n minus k. That cnk is the number of ways to choose which k of the trials are the successful ones. The p to the power k is the probability those chosen trials all succeed, and the 1 minus p to the power n minus k is the rest failing. And handily, the mean of a binomial distribution is just n times p. Let's use it. A machine produces items with a 30% fault rate, so p is 0.3, and we check a batch of 10, looking for the probability of exactly 2 faulty. So n is 10, p is 0.3, and k is 2. The number of ways to choose which 2 of the 10 are faulty, C10-2, is 45. So the probability is 45 times 0.3 squared times 0.7 to the power 8. Now 0.3 squared is 0.09, and 0.7 to the power 8 is about 0.0576. Multiplying 45 times 0.09 times 0.0576 gives roughly 0.233, about a 23% chance. And the expected number of faulty items is n times p, 10 times 0.3, which is 3. Picturing this binomial, we draw a bar for the probability of each number of faulty items from 0 up to 10, with p at 0.3. The distribution peaks near its mean, n times p, which is 3. It isn't symmetric because p isn't a half, so it leans to one side. Very high fault counts are still possible, but grow increasingly unlikely as you move right. And, as always, adding up all the bars gives a total probability of 1. Here's a neat one for the same machine, with p of 0.3 and n of 10, the probability of at least one faulty item. Rather than adding up loads of cases, we use the complement. At least 1 equals 1 minus the probability of none. The probability of none faulty is 0.7 to the power 10, which is about 0.028. So the probability of at least 1 is 1 minus 0.028, which is 0.972, around 97%. In other words, a batch of 10 almost certainly contains at least one faulty item. Notice that's the very same complement trick we met back in outcome 2. Let's set the two discrete distributions side by side. The uniform is flat with equal bars, while the binomial peaks near its mean of n times p. The uniform is about outcomes that are all equally likely. The binomial is about the number of successes in n trials. For the uniform, each probability is 1 over the number of outcomes. For the binomial, it's that Cnk, p to the power k, 1 minus p to the power n minus k formula. Their means differ too. The average of the values for a uniform and times p for a binomial. A fair die score is uniform. Faulty items in a batch are binomial. These aren't just textbook curiosities. In quality control, the number of defective products in a sample follows a binomial distribution. In surveys, the number of people out of n who say yes is binomial too. Uniform models turn up in games, with dice, in generating random digits, and in a fair raffle. The real skill is recognizing which distribution fits a situation, because that's what lets you calculate the risks and the expected counts that matter. Now to the most famous distribution of all, the normal distribution, a continuous, bell-shaped curve. It's symmetric about the mean, and because of that symmetry, the mean, median, and mode all sit together at the center. Most values cluster close to the mean, with extreme values rare in either tail. The total area under the curve is 1, representing all the probability, and the whole thing is pinned down by just two numbers, the mean, which sets the center, and the standard deviation, which sets the width. Let's dwell on that shape. The curve is highest at the mean, and falls away symmetrically on both sides. A larger standard deviation makes it wider and flatter. A smaller one makes it taller and narrower. The two tails edge ever closer to the axis, but never quite touch it. And the area beyond 3 standard deviations out is truly tiny. It's a shape that turns up again and again because so many natural measurements follow it closely. For a normal distribution, there's a wonderfully useful shortcut called the empirical rule. Fixed percentages of the data fall within set distances of the mean. About 68% of values lie within 1 standard deviation of the mean. About 95% lie within 2 standard deviations, and about 99.7% lie within 3 standard deviations. That rule lets us estimate proportions in our head without any complicated calculation. Picture those bands shaded on the curve, the 68%, 95%, and 99.7% regions nested inside one another. Values beyond 2 standard deviations, which is only about 5% of the data, count as unusual, and beyond 3 standard deviations, about 0.3%, as very rare indeed. Because the curve is symmetric, each tail beyond 2 standard deviations holds around 2.5%. Quality control uses exactly these bands to flag items that stray outside acceptable limits, the basis of within-tolerance checks in manufacturing. Let's apply it to real measurements. Adult male heights are roughly normal, with a mean of 175 centimeters and a standard deviation of 7 centimeters. So about 68% of men are within 7 of the mean, between 168 and 182 centimeters. About 95% are within 14, between 161 and 189 centimeters. A man of 189 centimeters is 2 standard deviations above the mean, so only about 2.5% of men are taller. And 196 centimeters is a full 3 standard deviations up, extremely rare. All of that comes straight from the mean and the standard deviation. To compare values from different normal distributions, we standardize them into a z-score. A z-score tells you how many standard deviations a value lies from the mean, and it's calculated as the value minus the mean, divided by the standard deviation. A positive z sits above the mean, a negative z below it. The beauty of it is that z-scores put everything on one common scale, and standard normal tables then convert a z-score straight into a probability. Here's where z-scores earn their keep. On test A, the mean is 60 with a standard deviation of 10, and you score 75. On test B, the mean is 50 with a standard deviation of 5, and you score 62. Which is better? For test A, z is 75 minus 60, divided by 10, which is 1.5 standard deviations above the mean. For test B, z is 62 minus 50, divided by 5, which is 2.4. So even though 75 is the higher raw mark, the z-score shows test B is the stronger performance. A z of 2.4 puts it in roughly the top 1% of candidates. Z-scores make different scales genuinely comparable. The normal distribution crops up remarkably widely. Naturally occurring measurements, heights, weights, blood pressure, birth weights tend to follow it. So do measurement and manufacturing errors clustered around a target value. Standardized test scores and IQ scores are deliberately designed to be roughly normal. And here's a deep one. The averages of large samples tend to be normal even when the raw data isn't, an idea that sits at the very heart of statistics. Let's finish by choosing between our models. The first question is always, is the quantity counted or measured? If it's counted, with 2 outcomes per trial and a fixed number of trials, you want the binomial, which is discrete. If it's a set of equally likely separate outcomes, that's the discrete uniform. And if it's measured on a continuous scale and clusters around a mean, that's the normal distribution. Choosing the right model is the real skill here because it decides which formulas and rules apply. Count versus measure is the quickest test. Let's pull learning outcome 5 together. A probability distribution lists each possible value and its probability, and those probabilities always sum to 1. The discrete uniform makes every outcome equally likely, like a fair die at 1/6 each. The binomial counts successes in n independent trials using CNK, p to the power k, 1 minus p to the power n minus k, with a mean of n times p. The normal distribution is a continuous symmetric bell curve, where 68, 95, and 99.7% of the data lie within 1 2, and 3 standard deviations. And a z-score, the value minus the mean, divided by the standard deviation, standardizes values so results from different distributions can be compared. And with that, we've completed both the outcome and the whole unit on foundations in statistics. You can now recognize a uniform, binomial, or normal situation, calculate with each, and use the empirical rule and z-scores to make sense of the normal curve. To round things off, Rowntree offers a gentle recap of distributions, while Crawshaw and Chambers gives fuller worked examples of the binomial and normal. The Royal Statistical Society's Significance magazine shows these distributions at work in real quality control and testing stories, and Corbett Maths has clear videos if you'd like the binomial or z-score calculations demonstrated once more. Well done for making it through. A little practice now will lock it all in.